All right, guys, we're going to go ahead and get started here. Good afternoon, everybody. Afternoon.
Oh, yeah.
Good to see you guys. All right. Well, I don't have really any announcements, I don't think. The only thing I'll say is the quiz this Friday is over two things we've already done. So if you could take that at any point, actually, it's over the female reproductive system and the stuff we covered on Monday. So that is ready for you at any point. Continuing on with the heart today, but yeah, any questions about anything coming up? Yeah, Lucas?
So this might be my fault, but I haven't checked syllabus yet. But the practical is not next week. I think that's what it says on campus.
Does it say that on the canvas? Like, okay, yeah.
But
I always,
like I said, I haven't checked.
no, thank you. I always go by this one, but there were some mistakes in the on Canvas that I tried to fix them all, but I might have not fixed that one. Let's see, where is the bio 1040 lab? Yeah, so the review is next week, and then practical is the week before spring break. So, but does the assignment for the lab practical and Canvas says next week? Is that right?
It does.
Okay. I'll fix that. Thank you. No, I didn't realize that. So thank you. Yeah. Yeah. Okay. Yeah. All right. Other questions at all or anything else? Okay. All right. Well, we're continuing on with the heart today. Today will be a little bit more of the physiology of how things work, specifically the kind of the electrical aspects of the heart, and then a bit about about the kind of rhythm of the heart. And so, yeah, let's dive into it. We're going to talk about the action potentials in the heart. We'll talk about two different types of action potentials we see in the heart. But before we do that, I wanted to review what the normal type of action potential that we already learned about last semester. So the type of action potential we'd see in a neuron or in skeletal muscle is one that looks like this, right? And so this is a slide from last semester, right? So we got our different phases here, right? We got our resting phase, our depolarization, repolarization, and hyperpolarization, right? The thing that causes action potentials are changes in the permeability of the membrane to ions, right? How open is the membrane to different ions? And then that's going to be dictated by voltage gated ion channels, right? So we see these permeability changes here. All right, we see the depolarization. Right around the time we see depolarization, we see sodium permeability shoot way up, right? Pretty much showing us that depolarization is caused by sodium moving, and in this case, it'd be sodium influx, right? And then we see the permeability of potassium changing right around the time that repolarization and hyperpolarization are occurring. So it's the efflux of potassium that causes those, okay? So that's just kind of the review of stuff we learned last semester. Questions on any of that? The other thing to note here is the x-axis. We're going to look at some other action potentials that are different here in a second, but this whole thing really only takes about 2.5 milliseconds, right? This whole x-axis is 4, right? But really we're kind of ending hyperpolarization at about 2.5 milliseconds, right? So we'll compare that to what it looks like in cardiac muscle in a second, which is a lot different. Okay, so the other thing that is related to all of this is how muscle cells contract, right? We talked about the sliding filament theory last semester. And all this with actin and myosin and troponin and calcium and all those things, right? Now we'll kind of look at that. It's a very similar mechanism in heart muscle cells, but not exactly the same. So we'll look at that a little bit as well. But again, we have this sarcoplasmic reticulum. It's really important in both types of cardiac muscle cells and skeletal muscle cells for releasing calcium. When we look at the length of that action potential and the refractory period, somewhere around 2 milliseconds, like we just pointed out on the last slide, okay? A single twitch of skeletal muscle might be around 20 to 100 milliseconds long. And in that single twitch, we get many, many action potentials occurring to get that one twitch that creates that tetanic contraction, that nice smooth force producing contraction that we talked about last semester. Okay, so this is kind of all just review of those things there. Give you a sec to finish writing that down. Okay, so then what about cardiac action potentials? Okay, so one of the things that's different about them is that they start in what are called pacemaker cells. Okay, so pacemaker cells are specialized cardiac muscle cells that are found in the sinoatrial node or the SA node, and then the atrioventricular node or the AV node. Okay, so these are cells that depolarize on their own. They don't need a nerve or a neuron to interact with them to cause them to depolarize. They depolarize on their own. Okay, so they're pacemaker cells. They're called autorhythmic cells, and we'll look at their action potentials in just a second as well. And so it starts there in the heart, and then it passes through those gap junctions that we've been talking about. Right, it goes from cell to cell to cell. So we don't need to activate every single little cardiac muscle cell along the way. It just spreads from the top of each chamber to the bottom of that chamber. Okay, so resting membrane potential is still going to be negative on the inside, just like it was in skeletal muscle. Okay, the inside of the cell would have more potassium, so lots of potassium inside, not much outside. Same thing as skeletal muscle. And then just the opposite with sodium. We have lots of sodium outside the cell and not much inside. Depolarization, the depolarization phase of a cardiac action potential is caused by the same thing, sodium rushing in, just like it was in skeletal muscle and neurons. Okay, so all this is the same so far, right? What's different though is there's a plateau phase in cardiac myocytes to cause that plateau phase. So we get the depolarization, big depolarization spike, but then it stays depolarized, kind of stays flat for a long time up top. And that's all caused by calcium coming into the muscle cell. So this is unique, right? This is not the same as skeletal muscle. Okay. And then eventually at the end of that plateau, it goes back down, it repolarizes, and that's still caused by potassium going out. So all of that stuff is really the same as what we talked about with skeletal muscle, except for this plateau phase, right? And then obviously except for these pacemaker cells and gap junctions. But yeah, Ava? Yeah, the reason it says it that way is because the if we'll come back to that slide, but with this slide, this is our depolarization, right? So this is sodium rushing in. This is caused by calcium coming in. They're both the same stimulus for those gates to open. The stimulus is depolarization spreading to this part of the membrane. It's just that the sodium channel opens up fast. All right. And so that makes that happen fast. And then the calcium channel is kind of like creaking open slowly. And by the time we're already up here with the sodium influx, now calcium starts coming in because it just took a little longer for it to open than it did for the sodium to open. That's what it means by that. Good question. Yeah. And it's the same thing with potassium as well, that it takes longer for those channels to open. So it takes longer for us to start seeing that potassium efflux. Good. Other questions on that so far? Okay. Yeah, so when we look at cardiac action potential, why don't you go ahead and just take a sec and just label what we just talked about, okay? So what's going on in 1, 2, and 3. And you can kind of check this out yourself, see if you have any ideas on how long that would be. And then you can send in this answer there in your clicker, just in a number format. Check with your team on that. Okay, go ahead.
But also I think one is. You might be good too. Yeah. Like, do you know what I mean? Like, where like there's always
Oh, so the.
transition.
All right, send in that number there, just 1, 2, or 3. All right, make sure to hit send on this type of question. All right. I'll leave it open for a sec just in case. Maybe just hit send one more time. I see 42. That might be about right. There we go. There's one more. Okay. Yeah, so let's walk through this. So step 1 there is our depolarization caused by sodium influx, right? Notice how straight up it looks, right? It looks completely straight up compared to like being a little bit of a slant in the other one that we just looked at. 2 would be our plateau phase caused by calcium influx. Okay. And then 3 would be our repolarization caused by stopping of calcium influx and the start of potassium efflux. Okay, obviously the answer to this question would be 2, place where calcium influx is happening. Step 2 there. Okay, if you look at the x-axis here, right, this goes all the way out to 300 milliseconds, right? So how long is the cardiac action potential? It's more like 250 milliseconds versus 2 milliseconds in skeletal muscle, right? So very, very different in terms of duration. And most of that has to do with that long plateau phase in the middle. Okay, the reason it's helpful in one way is we don't want to have these kind of long held forceful contractions like we do in skeletal muscle. We want one strong beat, one strong contraction, and then relaxation, right? So we're kind of preventing tetanic contractions. Whereas so the purpose of contraction of cardiac muscle is very different than the purpose of contraction of skeletal muscle. Right? Skeletal muscle, we're kind of producing a lot of force and holding it, right? Cardiac muscle, we produce a lot of force for just a split second, and then we let it go, right? And yeah, and there'll be some other applications of this too. We can notice right now that this has tension on this graph too. We'll come back to that. There'll be a clicker question on that in just a second, but just pointing that out for now. Questions on this so far? Okay, and this is just showing if we put these two action potentials on the same x-axis, how different they would look, right? So there's our regular skeletal muscle action potential, right, on the same x-axis, right? So very, very different in terms of duration, right? So we need hundreds of these to produce a single twitch in a skeletal muscle, where there's just one for the beat of the heart in kind of in each cell in a chamber of the heart. Okay, so go ahead and chat about this question with your people on your team, and then talk it through. You can look back on that graph, looking at how the tension is in that purple line and how it rises. But go ahead and decide what you think here, talk through these answers, and send in your answer. Wouldn't it be because
Maybe because we I have a question.
Yeah.
So, I'm confused. Why does it last like longer, but still the valves open close so quickly? Like, why is it that?
Well, I mean, longer we're talking 2 milliseconds versus 300 milliseconds. So it's still less than a second, right? It's still like a third of a second, so it's still very quick. So yeah, so it's still like kind of like the whole heart has to contract at once. So it's kind of like this, just kind of like all at once, like versus like a bunch of little action potentials happening to activate a muscle, and then it creates tension, and then like holds the tension versus like one solid like thing. So it's kind of like building tension as it's going, and then pushes it. But I don't know.
Thanks.
Yeah.
Thank you.
All right, go ahead and send it in if you haven't yet. Okay. Yeah, so about 90% of you are saying D. Okay. The tension building is related to calcium influx. Okay. Um, I guess that's somewhat obvious because it's happening during the phase where calcium influx is happening, right? And so electrically, a positively charged ion going into the cell is what's keeping it depolarized, right? So it's keeping it up there as far as just the voltage. Okay, so that's kind of one job that calcium is doing, but that's not the one that's related to tension. The one that's related to tension is what calcium does when it gets in there, right? What does calcium bind to when it gets inside of a muscle cell? We go back to this. What happens here? What's happening in here? Troponin, right? Yeah. So calcium not only keeps us depolarized, which is doing here, but then when it goes in and binds to troponin. And then each calcium that's bound to troponin means another myosin head can attach to actin. And so that's exactly why we're getting more tension, right? Is because as calcium goes in, it's binding to troponin, opening up another myosin binding site. Myosin can start, then that one can now start helping to add to the tension development. Okay, so that would be within a single muscle cell. As more calcium flows in, we get more tension. Okay, and then as this is taking time, we're also letting the rest of the heart catch up too, right? Because like the cells on the top we're starting to contract, and then the ones on the bottom contract as well. So we're kind of so that is this one is partially right as well, right? This is giving the heart time to contract all the muscle cells, right? So this is kind of be like what's happening inside of a single cardiac myocyte, right? We're getting more calcium in there, so we get more actin myosin binding, but then we're also giving time for the rest of the heart to catch up too, right? And so then, or the rest of that ventricle, let's say the left ventricle, to catch up. Okay, questions on that? Okay, so that kind of gets us to this idea that the way that heart muscle cells contract is a little bit different than skeletal muscle cells. Okay, so when it comes to excitation contraction coupling, that's how we prepare for contraction. That was one of the things we talked about last semester. Okay, so the action potential gets created on the muscle cell, and then it goes down the T tubules, right, to the sarcoplasmic reticulum. Calcium is released into the muscle fiber via that sarcoplasmic reticulum. Those things are all the same as skeletal muscle, but then the differences are this. Number one, the sarcoplasmic reticulum enters each sarcomere only once instead of twice in cardiac muscle. And in cardiac muscle cells, the sarcoplasmic reticulum just doesn't have as much calcium in it. So we don't have the ability to dump a bunch of calcium in from the sarcoplasmic reticulum. So the heart muscle cells have to rely on extracellular calcium to get us enough calcium to get that contraction to happen. Okay, so 10 to 20% of it has to come from outside. Where skeletal muscle, we don't have that at all. We don't have any extracellular calcium coming in to help with that change in membrane potential and the increase in tension by binding to troponin. Okay, so these are kind of three key differences in the way that heart muscle cells contract. Yeah. Okay, questions on any of that? All right. It's like most of you done writing. Okay. Yeah, so then let's talk about kind of this pathway of conduction, which you guys have already kind of worked through to get ready for the quiz. But we're going to start up with the SA node, the sinoatrial node. These are autorhythmic cells. Okay. This is the upper right atrium, right by where the vena cava come in. Okay. The function of this is to be the pacemaker of the heart. Okay. This one, yeah, so this is autorhythmic. And then we go down to the next part. So first of all, that activates, causes the atria to contract, and then it gets to the AV node. It causes a little bit of pause. So this is right at the tricuspid valve. So this is right at the line between the right atrium and the right ventricle. Okay. So it causes a slight pause, about a tenth of a second pause. That allows for a little bit more filling time. And then it's going to push that action potential down to the ventricles and cause the ventricles to contract. Okay. But on the way, it's going to go through the AV bundle. This is the top part of that interventricular septum, right? The wall of tissue between the two ventricles. That's the interventricular septum. The AV bundles are at the top of that. And then from there, it branches into two to go to the right side of the heart and the left side of the heart. All right. And those are the bundle branches. These are in the interventricular septum, but there's kind of two parts to it, right? So one on one edge of the septum, one on the other edge of the septum. And then finally, those Purkinje fibers that go and wrap around the base of the heart. Okay, so these are all throughout the ventricles and the papillary muscles. These help to contract the ventricles and the papillary muscles, and they depolarize super quick, 100 times faster than the rest. The reason they need to go so fast is because the top part of the heart is already contracting at this point, right? So we got to get that signal around the bottom part really fast so we can catch up and all those cells can contract at the same time, right? So we got to, the depolarization and conduction happens faster the further we go down the heart. Okay. Yeah, go ahead and label that next slide. I think most of you already have, but then you can also answer the question there on your clickers. I'll just give you a minute or so since you've probably labeled most of that already.
Yep.
Go ahead and check in with your teammates on your answer there.
Will the atrioventricular node need to be autorhythmic if it's like I know that if your SA node gets wiped out, like this can
Yeah,
also cause
take
it.
over. Yeah.
But is that why, or is there another reason why I'd be autorhythmic?
Yeah, there's actually autorhythmic cells kind of spread throughout even the AV bundle and stuff too.
Okay.
And so, yeah, I don't know if it's just kind of like backup. That'd be
But
my
they
guess.
fire at different rates.
Yeah, they do fire at different rates. There's actually this quick clicker question coming up is kind of getting at that. I'm going the wrong way, but yeah, this one here.
Okay.
Yeah, but they depolarize at different rates.
So like the SA node is like typical. So what would cause like tachycardia? Tachycardia.
Yeah, so it
Is
could
that
it could be that the AV node takes over, but yeah, typically the SA node is still driving it. SA node depolarizes the fastest. That's why that's the answer to that quick question. But yeah, but yeah, it could be that the AV node takes over, but then it's kind of not functioning properly, so it actually depolarizes faster than the SA node. It could.
But if they're functioning properly, although they're like autorhythmic, they will like take the lead of the SA.
Yeah, they'll get depolarized because the action potential hit them before they depolarized on their own.
Okay.
Yeah,
But potentially they would depolarize on that.
they would if they didn't have that stimulus hit them first.
And would their depolarization cause depolarization of the atria as well?
No, it doesn't really spread back the other way. Yeah, yeah. So you can
So
kind of get that
stay in
supraventricular tachycardia where it's just like the atria are not really doing a whole lot.
Yeah.
And yeah.
But is that like AFib would be caused? What would cause? So what would cause AFib?
Yeah, I mean it's a being kind of it's more like the conduction system and it's activating too rapidly. And it's not
But then
too
the ventricles could be normal because of the
Yeah, the AV
node?
node kind of slows it down and can kind of, yeah, it doesn't have to necessarily be driven by that completely because the AV node can kind of take over. Yeah, I don't know all the details of
Yeah.
that either, but yeah, it's a great question. Yeah, yeah. All right, send in your answer if you haven't yet. Okay, a couple more people need to hit send, I think, there. But yeah, let's walk through this. I'll leave it open. So A is the sinoatrial node, SA node. B would be the AV node. All right, C, we got our atrioventricular bundle before it splits into two. And then we got our bundle branches. And then finally, those Purkinje fibers, also known as the subendocardial conducting network. And so the one for the question here is B, the AV node. All right, questions about these? Okay. All right. So the way this kind of ends up working is, and we'll walk through this one together, is this is kind of a time-aligned cardiac cycle, right? And so we haven't looked at this one yet. We'll look at it in just a second, but this is what the action potentials for those autorhythmic cells look like. Okay, so this number one is the SA node depolarizing. All right, so that would be first. And then what do you think number two would be? That's the atria contracting, right? Or depolarizing, right? That's the atrial muscle contracting, right? Because the SA node causes the depolarization of the atrial muscle, right? So this is like the same thing as this, but just a small version of it because it's just the atria, not the big ventricles, okay? And then that spreads down to the next part that's pacemaker, right? And that's the AV node, right? So then we see the AV node then depolarizing and activating, okay? And then we get that little pause, right? There's a little bit of space between here, right? And then we get to the big ventricular muscle, and that is our cardiac action potential we've been looking at with the big plateau phase, right? So we're kind of seeing all of that together there with those. So the ventricular depolarization was the fourth one there, number 4. All right, ventricular muscle. Yep. Okay. All right. Questions on that? Okay, so then what we can kind of look at a little bit more detail is the way that these autorhythmic cells work. Okay, so these are cardiac muscle cells. They're just non-contractile, so they don't serve the purpose of producing tension in the heart, but they set the pace of heart contractions, right? And the locations are how we just talked about in the sinoatrial node, in the AV node. We also have some of them also spread throughout the AV bundle. And these can kind of serve as backup pacemakers if the SA node isn't working for some reason, right? And in these cells, the action potential begins on its own, right? So we don't need to have a nerve to activate this, right? So how many people know from the old Indiana Jones movie? I think it's the Temple of Doom, where the guy reaches into the guy's chest and pulls his heart out, right? And he picks it up and it's like beating in his hand a little bit, right? There's some truth to that actually, right? That the heart would keep beating for a little bit without any nervous system connection because of these autorhythmic cells. Autorhythmic cells, obviously, that wouldn't last long because there's no blood getting to the heart, right? And the heart would die pretty quickly. But there is some truth to that. So with these action potentials, there's no resting membrane potential between. Hyperpolarization that occurs between the action potentials is what leads to closing of potassium gates and then just automatically reopening of sodium gates. Normally, we need an external depolarization to open up sodium gates. In this case, it just happens by that hyperpolarization that occurs between action potentials. Okay, and that's going to lead to this kind of slow influx of sodium until and that's going to have it start depolarizing. Okay, until it hits a certain threshold. Once it hits that threshold, then we're going to get calcium influx next. Okay. And we'll look at this on the graph on the next slide. But then the repolarization is always the same with all the different types of action potentials we talked about. It's always potassium exiting the cell and that stopping of calcium channels or closing of calcium channels. Okay, so a little bit different here. We have kind of sodium influx first till we get to a threshold, and then we got calcium influx. And then for repolarization, we've got potassium efflux again. Okay, so the next slide just has you label those steps. So go ahead and do that. And again, you can answer the clicker question there.
Sneaker, would that send a signal to the, as in,
Yeah.
to send it, or does it just take place?
It's pretty much, yeah, they're usually connected to the top of the atrium. And so that kind of just takes the place of the SA node.
So so instead of like telling that node to send what it needs to, it just sends it on it.
Yeah, it's kind of
Doesn't it,
right.
like make the, like, I don't really know. I don't
Yeah,
really know.
it pretty much does the same thing. Yeah, pretty much. So like the wires go directly to where the SA node is. And if the SA node isn't functioning properly anymore to do it on its own, then those wires cause the depolarization of that area, which then spreads throughout the fibers of atria and then down to the AV node. Some of the pacemakers can connect to the AV node as well if that part's not functioning properly. But
Different ones.
Yeah.
Isn't there one that's like right under the skin or something, and then one that's like weaker?
yeah, I'm only familiar with the ones that are on the skin. Yeah, I mean, not like under the skin. You mean, is that what you mean, or on the skin?
I thought it was something that's towards like, it's like just under.
Yeah.
You can see it.
Well, you can see it's like a bump, but it is under the skin. And then the electrodes go through the chest down into on the side, not over here, yeah, down into the heart. But the little box is like underneath the skin right there. So you can kind of see it and move around. But
Well, really, my brother is, when I worked at the PT clinic, we had to ask if they had it before use system.
yeah, for sure. Yeah, that's smart. Yeah, and some of them have defibrillators in them too.
Yeah.
So then that can, if somebody is at risk of having sudden cardiac, um, yeah,
Oh.
asystole, then it can shock them.
I think in my ACLS class, they asked that if these were, if you would use an AED if they have one.
I mean, if it's working properly, then you wouldn't need to, but if it's not working, then you would probably still use the defibrillator, but it should do it on its own. That's if it's working right, but yeah, super interesting. All right, send in your answer here. Make sure to hit the send button on your clicker there. Go ahead and hit send. All right. So about 60% of you are saying 2, 20% of you saying either 1 or 3. So a little bit spread out there, but let's walk through this. So these are the action potentials of these autorhythmic cells or these pacemaker cells. We'd find the SA node, the AV node. Yeah, Ethan, what do you got? When do they close? Yeah, yeah. So pretty much right after this here is they're going to close, and then the calcium activates from there. So they're going to close. Yeah, kind of switches there. Yeah, and this is more of the sodium channels here lead to more of a slow influx versus what we're used to with really rapid influx of sodium with the other two action potentials. Yeah, so we see the slow depolarization due to sodium influx in one, and this is just the part that happens naturally, right? There's nothing that caused that, and then it hits that threshold there, right? And then that threshold is what activates the calcium channels, and that's what leads to that part there. All right, so number 2 is where calcium influx occurs. And then 3 is that repolarization that happens via potassium. And so then it's because of this getting down here to this hyperpolarized state, that's what then closes the potassium channels and reopens the sodium channels So then it just starts back up again and starts letting sodium in again right away and moves into the next action potential. Okay, so we've really got three different types of action potentials, right? The one we learned last semester, the skeletal muscle and neurons, kind of all look in that way with that spike and come back down, last about 2 to 3 milliseconds. And we've got the cardiac ones that have the big long plateau on top and then come back down. And now we've got the autorhythmic cells with this difference between calcium and sodium influx for the depolarization. Yeah, Ava?
They have the action potential, and then that stimulates the SB node, the SA node.
Yeah, well, let's go back to this one here, right? This is really the flow of it all, right? So these are the autorhythmic cells in the SA node, and that looks just like the one we were just looking at, right? Those depolarize, which is what activates the atria, right? And they depolarize and the atria contract, and then that spreads to the AV node from there. Then we see another autorhythmic cell depolarization, right? And then that spreads to the ventricles, and then this is the ventricles contracting. Yeah. Okay. Other questions or comments on this? Okay. Let's do this clicker question here. Go ahead and chat about this with your team and send in your answer. This is the part of the class that really overlaps with XFIS. So. Yeah. For sure. Yeah. Totally. All right, send your answer in if you haven't yet. About 10 more of you, it looks like. All right, almost got everybody. You guys are all over the place for sure. We got a quarter of you saying A, 15% saying B, another quarter saying C, and 35% saying D. So this one is the correct one here. If they're all depolarizing on their own, right? It's the one that depolarizes first that's going to end up controlling the heart, right? And so that means the one that depolarizes the fastest, right? So the SA node depolarizes, right? If we go back to this image, SA node depolarizes, sends a signal to the atria. The AV node is still in the process of depolarizing, right? And then it receives the signal from the atrial muscle before it actually fully depolarizes, right? But then it does kind of pause there for a sec and then gets to the ventricles. But if the SA node isn't functioning properly, then the AV node could take over. It would just be a little bit different rate than normal, right? But the nervous system can help control that as well. So it's just that it depolarizes faster than the others, and the SA node depolarizes at pretty much 100 beats per minute. Yeah. Yeah, so really the correct term for that is conduction. So the Purkinje fibers are faster at conducting electricity versus, and I may have mixed that up. I might have put depolarization, but yeah, so it probably should say conduction. Like it just means that the signal spreads through that area faster. And because we don't really have autorhythmic cells in that area anyways. So yeah, good question. Other questions? Okay. All right. So the way that we measure this electrical activity in the heart is with an EKG, right? EKG, the K part is from the German language. Cardiac in German is with a K, right? And so that's why EKG is the typical way. That's where the technology was developed. But ECG is also fine for more of the English spelling of cardiac. Um, and really, what this is measuring is voltage, right? And so voltage, as we talked about last semester, is potential energy, right? It's a difference from in charge from one location to the next, right? And so we put all these different pads on people, right? For a 12 lead EKG, there's 10 different pads you put on, but it's just looking at two at a time. So things like this, right? And looking at the voltage between the two poles, the charge difference between the two poles. And so this is picking up depolarization and repolarization, all those things. And so the typical strip looks like this, right? We have this first little wave here called the P wave. That's atrial, that represents atrial depolarization. That's right around the time the atria contract. Okay, then we have this QRS complex. The QRS complex represents the ventricles depolarizing, which corresponds with their contraction. And then the T wave is when the ventricles are repolarizing. So that little bump at the end is ventricular repolarization. Okay, we're missing atrial repolarization because it happens during the QRS complex. And so we just don't see it because it's kind of hidden in there by those bigger fluctuations that happen in the ventricles. Okay, so this is very common to use in cardiac or in clinical settings to detect cardiac abnormalities. For the most common one would be ST elevation. All right, so if this line moves upwards, then that's a sign of a heart attack. We've heard the term STEMI, maybe in the hospital shows you watch. The Pit. How many people watch The Pit? We got some. The Pit's so good, right? Yeah. They probably talk about a STEMI coming in, right? STEMI, ST elevated myocardial infarction, right? So that's what it's talking about is that elevation in the ST segment. And a myocardial infarction is a heart attack, right? Yeah. Easy. Yeah, it would just be like boop, like up here instead. But it totally depends on which lead you're looking at too, because some of the leads are flipped upside down, depending on which way we're looking at the heart. And then ST elevation would look like the opposite; it would go down. And then sometimes you have ST depression as well. It all depends on kind of which angle of the lead, angle that the lead looks at, and then where the damage in the heart is too, because each lead looks at a different part of the heart from a different aspect. So it's super complicated and I'm not an expert at interpreting them, but yeah, yeah. So other questions on that? Okay. All right. Well, we're going to just walk through a little bit of an activity here on the cardiac cycle and kind of looking at how to make sure we kind of have our head wrapped around everything that goes into each step of where the blood goes, but also the contraction and relaxation of each. So what I'd like you guys to do first is take these images here. Okay. They're not in the right order. Okay. But I want you to kind of work through with your team and get them in the right order, starting with passive atrial filling. Okay, so passive atrial filling would be before the atria contract, but they're just filling up with blood. Okay, make that your starting point. And then your last one that you're going to choose is when the ventricles relax. Okay, so just kind of walk through that with the people on your team. See if you can come up with the correct order for that. Okay, based on where the blood is, the little arrows represent contraction. Okay, so little black arrows represent contraction. Okay, go ahead and work through that. And yeah, and see, yeah, I'll have you send it in on your clickers as well, the right order of the letters there.
As you said, it's possible.
Yeah, I think it's B. So I think.
Wait, what about A?
Oh.
Oh, C A. Oh,
CA.
A.
I don't want to have you spend all that time typing those in on the clickers, so just send in the last letter on the clickers. Mhm.
I like that the two pieces are aligned.
Talking to Maddie about that too. It's like, this is the place where there's a lot of overlap, so it helps you guys. Yeah.
What did he say to what?
Yeah, what do you need to study for which class? Yeah, for sure. Mhm. Are you an EMT even on too or no?
Oh, yeah.
EMT, yeah, that's what I thought. Okay. You
Yeah.
learned a little bit of EKG, but not much. Huh?
I know,
Yeah.
yeah. I'm kind of hoping to do a PALS course.
Mm,
And I think they teach you a little bit more EKG stuff.
yeah.
But yeah, with us, they're like, so like this measures the heart,
Yeah.
smoke over fire,
Okay.
still on grass, or whatever.
Okay.
And they're just like,
Yeah.
we like learn the placement, but that's
Where?
it.
Yeah, how to put them on.
Yeah.
Yeah, then the paramedics have to interpret it for them.
No, actually, do
Or
you
not
know
even-
much about like the PALS courses or the pediatric advanced life support?
Yeah, I've heard about that stuff.
Okay.
Yeah.
Yeah, because I was
There's also like
recommended.
ACLS too.
Yeah, I
That's-
was recommended both of those for like preparing for an ER tech job.
Mhm.
But I was like, I don't know if I want to like toss that on top of my course load right now.
Yeah.
So I was like,
So,
maybe I do
yeah,
it
so pretty, they can be pretty intense for sure. I know ACLS is pretty intense.
Seems so cool. though.
Yeah, super
I can
cool.
imagine how cool it'd be to like have a little better understanding of like the code and stuff.
Yeah, totally, totally. Yeah. All right, send in that last one there. All right. Okay, so most of you are saying B is the last one. Let's walk through it. That's the same thing I got. So what do you start with? Where's the passive filling? What's our starting point? C. Yeah, good. So we got C here. Okay. So let's just do it this way. So we got C. Okay. Um, C, we can see that the AV valves are open, right? Blood is passing from the atria down into the ventricles. Okay. Then what's next after that? A. A is next. Good. Okay. So we got A. Some of you said that. A is next. That is just pretty much the same things happening, but now the ventricles are pretty much full, right? It's just continuing that, right? So the ventricles are pretty much full now. Okay. And then we can go to F, right? Because F will be where the atria contract. This is called the atrial kick, right? So this just kind of shows you that the atria don't fill up and then contract and move all the blood to the ventricles. That's not how it works. That's a lot of times how we picture it, I think, right? Atria fill up and then move blood to the ventricles and then they fill up and then move blood out. It's not the case, right? We have these valves are open for a while and blood is just going through the atria. They're kind of like big blood vessels for the most part, right? They're letting blood go through. And then we get the atrial kick at the end in F, which pushes the rest of the blood down to the ventricles, okay? And then from there, what'd you guys say was next? Echo, thank you. Yeah, exactly. E, perfect. Okay, so now we got some ventricular contraction, right? But this is contraction that isn't enough to open up the aortic valve, right? We'll talk, you don't need to know the names of these, but this is called isovolumetric contraction, which means there's no change in volume yet because we haven't opened up the valves, right? But we're starting to produce pressure in the ventricles. But look, the aortic valve and the pulmonary valve is still closed, right? So we haven't opened up those valves yet. Okay. Now, what do we got left? We got one more. Delta. Thank you. Yeah. So D, we got D here. Okay. Now we've opened up the valves. We've produced enough pressure to open up the valves. We start ejecting blood from the right and left ventricles, right, to exit the heart. Okay. And then as yeah, most of you said on the clickers, you said B. Bravo. I thought you said bravo. Yeah. Okay. Yeah. Yeah. So, and now we're here, right? So now we're here. And we do start to fill the atria a little bit here, right? These valves aren't open yet because we still have pressure here. Okay. And then the ventricles are going to relax to move us back to C. And then that's what opens up those AV valves again. Okay. So yeah. So then with that all in mind, see if you can kind of fill this in, okay? And yeah, and actually we'll just do it together because we don't have much time left, but let's just do it together. So when do the AV valves close? Okay. The one here, AV valves closing is at E. Okay, so E there. So what causes the AV valves to close? It's ventricular contraction. Okay, so, and we already talked about this, right? When the ventricles contract, it pushes blood up underneath the mitral valve and the tricuspid valve, and it snaps them shut. Okay, so we're seeing that happen there in E. Okay, when do the AV valves open? This is going to be in C, right? Because we were going from B to C, right? And this happens when the pressure in the atria becomes greater than the pressure in the ventricles. And that happens because the ventricles relax and the atria are filling with blood. So when the pressure in the atria exceeds the pressure in the ventricles, that's what opens up the AV valves. Okay. When do the semilunar valves open? Okay. This is in B. Right? Is that right? No, that's not right. B. Where is it? Yeah, it's T. Why do I have B there? Yeah. It is D, not B. That's when they close. B is when they close. D is when they open, right? So we've got yeah, D, this one right here, right? We're seeing the contraction, but it's not the first part of contraction, right? The first part of contraction is what closed those AV valves. That was an E, right? And then we build up more pressure until we open up those valves. So the deal here is the pressure in the ventricle exceeds the pressure in the aorta. If we're talking about the left side of the heart, that's what opens up the aortic valve, right? Picture that. Pressure pushing up against the aortic valve. There's pressure out here, which is your blood pressure, right? We need to make more pressure in here than is out here. And when that happens, then it opens the valve up, right? And lets the blood eject, okay? And then those semilunar valves close in the one right after D, which one was that? Was that B? Is that what we said? Yeah, that's what we said was B. And that's when the pressure in the ventricles becomes less than the pressure in the aorta, right? And that's when the ventricles are starting to relax and the blood just turns right around and comes back to the heart and snaps the aortic valve shut. Okay, so P waves should be occurring right around the same time the atria contract. So which letter would we put there? F, got it. QRS complex should be both D and E, right? And then the T wave occurring would be the one that happens after contraction, which would be right around B. Okay, so you might not be totally grasping it all yet because we're talking doing a lot of stuff fast here, but this is good stuff to come back to and kind of work through this to make sure you're understanding it. Okay, one thing related to this is this. We'll just briefly look at this diagram called the Wiggers diagram. And really what this helps us with is understanding what causes the aortic valve to open and close. And so what we see here is this is a time-aligned sequence of events in the heart. Okay, so we can see our EKG strip up here. That corresponds with pressures, right? The purple line is the aortic pressure, so that's the pressure outside of the heart. The green line is the pressure that the ventricles are making. And the blue line is the pressure that the atria are making. Okay. What you can see here is the aortic valve opens right here and it closes right here. Okay. So just like we said on the previous slide, ventricular pressure is rising at the same time the QRS complex happens, right? So this is ventricular contraction. So rising, rising, rising. When it gets higher than the aortic pressure, aortic valve opens, right? So this whole period of time, blood is ejecting from the heart, right? And now right about at this point, it starts to relax, right? So relaxing, relaxing, relaxing. Once it dips below the aortic pressure, the aortic valve closes, right? That makes the blood just turn right back around, come back to the heart and snap it shut. Okay, so what caused the aortic valve to open is pressure in the ventricle greater than pressure in the aorta. And then it's just the opposite down here. Pressure in the ventricle is less than pressure in the aorta. Okay, real quick here. These two things are the heart sounds, right? The lub and the dub. Okay, S1 and S2 are the two main heart sounds. Okay. You can hear it. There they are. Lub dub. Okay. So these are happening. The first one, the lub, is happening because the AV valves are snapping shut. We said that was because the ventricles contracted. So it was that one right there, right? Ventricles contracted, pushed blood up underneath the AV valves, snapped them shut. That's our first sound. That's our S1 or lub. Okay. The second one is dub. This one is occurring at B, at the end of ventricular contraction, when the blood turns around and tries to get back to the heart and snaps this aortic valve shut. All right, so that's our second sound. Okay. All right, guys, we got it. We'll see you guys on Friday. Have a good rest of your day.
Yeah.